Good morning, good afternoon, good evening, depending on the time zone you are in right now. Welcome to the 7th Excelero webinar of this year, using NVMe flash storage to maximize database performance. For this webinar, I have as special guests Brian Dougherty, the CTO at CMA Technologies, and John Kim, Director of Storage Marketing at Mellanox. As said in today's webinar, we're going to focus on databases, which are notoriously hungry for fast storage and demand very high IOPS and throughput. And as those database servers become faster and as workloads become more demanding, traditional flash storage technologies don't always keep up. So today you will learn how to architect a distributed flash storage solution that accelerates both traditional SQL and distributed non-SQL databases to achieve faster business results. Before I pass it over to John, I would like to share a couple of things with you. Everybody but our speakers will be on mute. We do want the webinar to be interactive though, so at the bottom of your UI, you should see a Q&A button. Feel free to post as many relevant questions as you want. We will be answering some of those questions during the webinar, but the most interesting questions we will save towards the end, and I will present them to our speakers so that they can answer them for everybody. With this, John, the floor is yours.
Tom, thank you very much. Hello, everybody. This is John Kim from Mellanox, and today we are going to, as Tom said, address the issue of how can you use NVMe Flash to accelerate database performance. I'm going to talk a little bit about the technology in the background, about how the networking and the storage can help you accelerate it, and then Brian from CMA is going to give an actual example of a solution that accelerates data performance using flash storage, as well as how a customer has implemented the solution to get that faster performance. So first, a brief one-slide commercial about Mellanox, who we are, for those of you not familiar. We are an enterprise and data center networking company. We've done, in our last year, we did about $1 billion of revenue. We have about 2,800 employees, and there's currently an announced plan for us to become part of NVIDIA. But for today, we are still a separate company called Mellanox, and we specialize in all sorts of high-performance networking, both Ethernet and InfiniBand, ranging in speeds from 10 gigabit up to 200 gigabit, and in fact, even up to 400 gigabit on the switches. So we do the adapters, we do the cables, we do the switches, and some related software. But enough about Mellanox. What's going on in the world of data, and specifically with databases, and how is this affecting the need for storage and storage networking? So not surprisingly, the amount of data out there has been growing very rapidly. It's growing not linearly, but in fact exponentially. I think everyone's heard this. But as this data grows, this also means that customers want faster data processing, especially on the database side. They have bigger data, more data, and they want faster storage. So they're implementing more flash. And in fact, they're also implementing faster networks. And if you look at this chart, we can see that if you look across all the server shipments and the switch shipments, that the faster networking speeds are starting to take over. If you look at this transition, there was, for a while, some years ago, there was a fairly slow transition from 1 gigabit to 10 gigabit and 40 gigabit. And that took several years, actually took a long time. But now there is a much faster transition happening where people are going from 10 gigabit and 40 gigabit over to 25, 50, and 100 gigabit. And in fact, there are even a few servers out there today that are already running 200 gigabit networking in order to get the most performance, because it turns out the newest multi-core CPUs and the fact that now many of these servers support PCIe Gen 4 and they're able to use faster flash, we'll get to more about flash in just a second, means that in many cases you need 100 gigabits a second, and in a few cases you need 200 gigabits a second in order to get the most value out of your new servers. So let's talk specifically about databases. So everyone has databases. There are many kinds. There are traditional databases, there are NoSQL databases, there are Hadoop type databases. But a key is that all these databases have to handle more data. There are more devices out there generating data from the Internet of Things, from whether it's structured or unstructured. It could be video from surveillance. It could be electronic transactions from e-commerce. It could be data collected from sensors, information collected from from all the many virtual machines out there. So more virtual machines are sending out more data that needs to be logged or stored or analyzed. So there's just a lot more data, and customers are generally expecting to do more real-time analysis and more artificial intelligence and machine learning with that data. So in the past, you might have had a big data lake or a big data warehouse, and you said, once a month, let's run some analysis on this, and I can run this analysis. It can take 2 or 3 days to run, and that's okay. So I didn't have to have the fastest storage or the fastest networking. But more and more today, customers are collecting all this data and they're saying, give me an analysis right now. I want to know what's my best selling product. Which of my sites is most likely to have an issue? Which customers are the happiest and which customers are the most likely to leave and go somewhere else? So there's a lot of need to do this very fast analysis or even real-time analysis in databases, where very quickly the database team has to be able to say, which ad should I serve, which product should I sell, which coupon should I send, where should I send this vehicle. So that analysis needs to be done very quickly, and this means that the database engines or the database products want a very low latency response. Very low latency from the database, which means that the storage has to be very low latency. So when we say faster response times, the databases have to respond quickly to the application or to the transaction, but this means the storage has to respond very quickly. And that actually also means the network has to respond very quickly. So in order to deliver this faster database performance, what people are doing is they're generally going to a scale-out solution. Usually they're going to a scale-out database, and they're running on a scale-out storage solution. And this means they get better performance, so they can handle more transactions, but it also usually means they need a very scalable, high performance, low latency network to go with it. They're also deploying more flash. So I'll get to that in the next slide. But a lot of flash, the fastest flash, more flash, and looking for faster, more efficient ways to get to that flash storage. Because flash is, someone said recently that flash is like the crack cocaine, or I guess the opioid addiction of databases. Once you start using flash, you can't go back because it just improves the performance of the database so much compared to using hard drives. So we know what we want to do with the databases and we know what we need. Now, how can we get there? So first of all, on the flash world, clearly we can go to NVMe flash. So before you had hard drives, then you had flash, which was connected with a SATA or SAS interface, and that was much better than hard drives. But then along came NVMe, non-volatile memory express. What NVMe does is it creates a faster, more efficient way to talk to those SSDs, to talk to the flash. It's a thinner, more lighter weight, efficient protocol designed for flash, as opposed to SAS and SATA, which were really originally designed for spinning disk. As a result, and you can see here, this is tests done by the Non-Volatile Memory Express organization, using NVMe flash gives you higher throughput, lower latency, and therefore with databases, more IOPS. And while some databases and some database operations do require high throughput, the vast majority of databases are looking for high IOPS and therefore looking for the lowest possible latency on the storage and the network. So I've got these great NVMe SSDs. They're very fast. The vendors have a faster interface, so therefore they've been building faster SSDs. But if I just stuff a bunch of SSDs into my database server, it's not always the most efficient way to use it. So first of all, I can't share these SSDs, and I may have stranded capacity. If I have 8 database servers, running in a cluster, and then I put the same amount of flash in each one, as the workload shifts, as different tasks or assignments or queries are put in, it's highly likely I'll end up with 6 of those servers have too much flash and 2 of them don't have enough. And with regular local flash, you can't share it. So that means you have to buy extra flash. You do over provisioning, which is a fancy way of saying I buy too much flash storage for every server just because some of them might need it, even though most of them won't. Also, when you use local flash in every server, it makes it very challenging to do a backup. It makes it hard to do replication. It makes it hard to share data. What if I have different database instances that need to read the same data? So backup, replication, high availability, and efficiency all are very challenging when you use regular local flash. Well, what about a traditional SAN? So in the past, if I had a single database, instance database server, I might run a big fiber channel SAN. And I would say, well, it's expensive, but it's fast and reliable. The challenge with that today is that compared to local NVMe flash, most traditional SAN or enterprise arrays are not that fast. They have a lot of software and overhead and protocols inside that potentially could slow down the performance. So we see that if I have a traditional SAN, which uses NVMe flash, it often is taking the latency maybe 2 or 3 times higher than just using local NVMe SSDs. So it has all the manageability and the backup and the replication, but it comes at a high price. I don't want to have to install a separate expensive fiber channel network, and they are quite expensive these days. And it doesn't give me the fastest possible performance, from those SSDs. So what is the answer to this? I need fast performance. I have this really fast flash, but a traditional, the easy way of putting the local flash in is not that easy to manage or efficient, and the way of using a traditional SAN is expensive and doesn't give me the best performance. There's also an issue of the networking. I've got with regular SATA SSDs, maybe 10 gigabit networking was enough. But even a few SSDs, if I'm trying to access them remotely, might overwhelm the 10 gigabit network connection. And then SAS SSDs were a little faster. So one SAS SSD potentially could fill up one 10 gigabit connection. That's great unless I have a server with 4 or 8 or 16 SSDs, and I'm trying to access that from another server, or from going from the database server to the storage. Now suddenly a 10 gigabit network connection is another bottleneck on top of this faster performance. So when we get to these NVMe SSDs I talked about, it's a faster interface with a faster SSD. This bottleneck becomes even worse because you have an SSD that can deliver 20 or 30 gigabits a second maximum, and the network connection is only 10 gigabit. So clearly the answer in this case is, as the SSDs get faster, you also need faster networking to do it, and that typically means servers these days are running 25 gigabit or faster, or 50 or 56 or 100 gigabit networking to get the most performance, depending how much flash they have and how fast the servers are, and how much data you're pushing through to your database. On the storage side, part of the solution is to create a more modern scale-out storage architecture to feed your database. I said that the more scalable databases are scale-out, whether that's Oracle or whether that's a NoSQL database like a MongoDB or a Cassandra. All of these solutions are now scale-out. So the storage should also be scale-out, and it should support NVMe SSDs. And in fact, it should be designed around SSDs and flash, and in fact, around NVMe SSDs for the best possible performance. So traditional storage is, again, usually designed around hard drives and then just modified to support SAS SSDs, and then they plug in NVMe SSDs. But the design still has some limitations. So a newer solution, like the Excelero NVMesh, is really designed from the beginning for flash and for scale out. It's designed around data center scale. So it gives you the option to set it up as disaggregated storage, where the storage is separate from the servers, or as a converged solution, where every server has the flash and the Excelero software running inside, so you can get maximum performance, but still share that storage across different servers. Because it's optimized for flash, there is basically little to zero CPU overhead, and you don't have to worry about the noisy neighbor problem, where traffic on one server is going to hurt the performance of an application on another server. So with this type of scale-out solution, you get very low latency, you get high performance, you get scalability, but you also get manageability. So I talked about how if you just have local SSDs, they're hard to manage and protect. But with a solution like Excelero's NVMesh, with the software on the servers, you get that high performance, but you also get the enterprise storage management tools that you're typically looking for when you have data storage for databases. You need reliability, you need the ability to provision and manage the storage, expand it when your database gets bigger, and so forth. So this is a more efficient storage solution. It relies on high-speed networking and high-speed flash, and it can really accelerate your database traffic. So one last look at this Excelero solution. And by the way, we've been very impressed by how well Excelero uses not only the flash, but they're also very efficient about using the networking technology as well. So you're able to have your servers with the flash in it. You're running Linux and the Excelero NVMesh software on it. You create volumes, and then you can have file systems if you need them. And you can also have all these different kinds of databases that run on top of it. So you can see that just about any database can be run on top of Excelero and get that performance acceleration. And then, not surprisingly, as a network vendor, Mellanox is very happy to supply high-speed networking to the database server and to the Excelero nodes. And again, those can be separate storage nodes, or they can be part of the database, running in the database server nodes. So Mellanox is an expert and industry leader at delivering that high-speed networking. So we are the world's biggest, have the highest market share in high-speed Ethernet adapters, as well as high-speed InfiniBand adapters. So anything from 25 gig and faster, we are the world's #1 vendor for these adapters. We also have some very intelligent and flexible switches, which have lower latency and easier management. And in fact, these switches are in many ways optimized for storage networking and can be used to accelerate database performance, either again, InfiniBand or Ethernet. And then of course, we also make some very interesting smart NICs and some very reliable cables and optics. And the final message about what Mellanox can do, and something that we've been working with Excelero on, it's it's being demonstrated, it's not quite ready it's not shipping yet, but is we have a smart NIC called the Bluefield Smart NIC, and this allows us to go and put the smart NIC into the servers, and it can run some of the Excelero software on the smart NIC and offload other tasks so that more of the CPU is available to run the database. So again, this is increasing that efficiency. So Excelero's got a super efficient solution, and by using our smart NIC, we not only give them the high-speed networking, but also the ability to run some of their software on the smart NIC instead of the CPUs. That means more CPUs for the database. That means a better, more efficient database solution. All right, I'll go ahead and this slide I think I already talked about it. So I'm going to skip over that, and that's the end of my section. Tom, I'd like to hand it back to you and Brian.
All right, John, this was very informative as always. Folks, if you have any questions for John, please don't hesitate to post them here, but I will ask them to John at the end of the session. I can already see Brian's slide come up here, so I'm assuming that Brian's ready for us. Brian, if you are, the floor is yours.
I am. Thank you, John. That was a great introduction, and thank you, Tom. Thanks, everyone, for being on here. My name is Brian Dougherty, CMA Chief Technology Officer, and we wanted to talk today about how we leverage great technology from Mellanox and from Excelero to provide a significantly high bandwidth Oracle RAC cluster database platform. First thing we want to do is we're going to talk about a customer use case. So we're going to give you a real live use case of an applied implementation of the product, our Mosaic software-defined NVMe Oracle RAC cluster that's being used at one customer, one of our larger customers. We're going to describe that solution in more detail, a little bit depth. We're going to talk about the evolution, how we got here. So we've been building these types of clusters for about 25, 30 years now, and there's been kind of an amazing evolution of the technology to where we've gotten to the point now where we think we have a really great platform that's flexible, low cost, and provides a great compute platform and a complete platform for an Oracle RAC solution. And we're going to give you some metrics on proof of performance metrics of the platform. So the first thing we want to do is kind of state the problem. And the problem shapes up as this. This is one way to view it. And it's what I'll call the Oracle Database I/O problem. And this is a problem that's been really in the industry for 30 years, and it's been the de facto problem that anyone building very large-scale Oracle databases or any database has been dealing with. And one way to view this problem is looking at it across two dimensions. On one dimension, we're going to take a look at bandwidth, and if bandwidth goes from 0 to infinity on this graph. And we're going to take a look at latency, as latency goes from kind of the traditional 10 millisecond, 2 millisecond, down to 2 millisecond for a single block I/O, down to a latency of theoretically 0 milliseconds. What the database problem looks like. If you look down on the lower left-hand quadrant, this is traditionally where we've been fighting for the last 25 to 30 years. And really the issue is, for the larger databases, at runtime, how do we reduce that physical search space? When someone issues a query, how do we take a very, very large database and make it look much smaller so that we can get in and out of that database quicker? And traditionally what's been done for these Oracle RAC databases is there's been a proliferation or explosion in the database side. So when you take a look at the physical to logical database size, meaning what are my physical database objects relative to what the business size of the database is. In other words, what columns and attributes I need out there just to support the business analysis itself, we've seen about a 3 or a 4 to 1 explosion. So what people are doing is we're building, architects and designers are building a lot of indexes. They may be building redundant tables, and certainly with Oracle, they're building materialized views. So there's a lot of derivative objects that are built that are out there just for the purpose of projecting at runtime a smaller physical search space to get the same information value. And why is that a problem? It's a problem because it proliferates storage. So rather than have a 50 terabyte database, in fact, at a lot of customers, you may have 100 terabyte or 150 terabytes. So the storage costs are more. The maintenance costs are much higher. You have to maintain these derivative objects that are there. If you build a materialized view that is a smaller representation of a large fact table, you may have to build the whole thing a night, or at least you have to incrementally build it. So it takes longer for you to refresh these databases. The maintenance windows are increased. And the other thing that happens is the query plans tend to move from more of a deterministic to a non-deterministic manner. By that I mean the query response time and the variability of the query response time becomes much more unpredictable. If someone runs a query one time and a plan actually uses an index and it's the right decision based on a cost-based optimizer, it comes back quick. But if they run it another time, these are very complex plans that are produced. It may take much longer. So the user is kind of confused with this. If we look at the Mosaic SD, our Oracle RAC cluster, using Mellanox and NVMesh, we're kind of up in the right-hand quadrant, and we'll show that with this customer. In other words, we've been able to reduce and get rid of all of these derivative objects on this implementation of this Oracle RAC platform because our bandwidth is so much higher and our latency is so much lower. So in other words, if you have a 1 terabyte table and it takes you 60 minutes to scan that table, that's much different if you have a 1 terabyte table and you have bandwidth that's a terabyte per second. That gives you much more freedom. So you end up with fewer objects, smaller databases, reduced storage, maintenance cost goes down, you can load it quicker, and you have very fast response time. And probably most importantly, it's deterministic, meaning that it's predictable query response time because the Oracle Optimizer itself has, believe it or not, fewer options to consider, but they're very reliable options. If you overlay this graph and you take a look at kind of where the traditional platform vendors have been for the Oracle RAC platform, and you break it into 4 quadrants, most of them have been somewhere in that low bandwidth, high latency to kind of moderate bandwidth, moderate latency area. So there's a lot of solutions using market-leading storage array vendors that may give you 5 gigabytes, 10 gigabytes, 50 gigabytes per second of scan bandwidth, and they'll give you a couple milliseconds per 8K block, 2 milliseconds, 1 millisecond. But that's kind of where most people are. With our solution and using NVMesh and the Excelero, we're kind of in that high bandwidth, low latency, ultra low latency quadrant. And that gives us a lot more flexibility. In other words, we're dealing with hundreds of gigabytes for a very, very kind of moderate size implementation per second of bandwidth scan capability. And we're doing it in 50 microseconds to 75 microseconds for an 8K block. So again, it allows us to get rid of all those derivative objects, and it allows us to be have much more deterministic set of plans. If you look at a vendor such as Oracle's Exadata, which is a very good solution, Exadata, the difference between Mosaic and our solution here in the Exadata is that our solution, we believe, is much more predictable, and it doesn't really rely on very complicated software on the cell server and the storage server to get that speed up. In other words, if you look at Exadata in 3 different characteristics, if queries go into an Exadata platform, the Exadata platform may or may not be able to push that predicate and that query all the way out to the cell server. And it may do that with one query, but on the second query that comes down, it can't do that. and much more of the data has to go up into the compute platform itself. So it becomes a much more asymmetric response and delivery, and it's more complicated from a software maintenance perspective. And so the solution that we're providing is going to provide a much simpler, a much higher performing, and a much more symmetric solution. So if we take a look at one of our higher-end customers that we have, this is one of the largest Medicaid recipient states in the country, in the U.S., and they're using this to provide analytics to millions and millions of healthcare recipients with over 20-plus billion rows of claims data out there. They're processing terabytes of new claim data per year, and they're really servicing thousands of analytic queries, users running thousands of queries a day. So what is the solution they're using? Mosaic SD NVMe is an Oracle RAC compute cluster using this great technology from Excelero and Mellanox to provide this platform that they're running on. It's a purpose-built database platform. It's pre-calibrated, pre-configured Oracle platform. That takes out the risk of the solution. It's a very well-balanced solution between, if you look at compute, storage, and interconnect. The architectural components can be broken down into a compute, storage, and interconnect. The compute can be any x86 server that's there running Linux, either UEK or Red Hat. The storage is state-of-the-art NVMe drives, flash storage, can be from different vendors. And the Mellanox technology and the Excelero technology are key components. Mellanox in the both the client and the storage server side in terms of the cards, the ConnectX, the RDX that are there, and obviously the switching technology and the software technology, and of course the NVMesh as both the client, the scale-out software-defined infrastructure that we're leveraging for this solution. We also include with this solution, if you drop in a new platform, you've got to get your database from an old platform to this platform, and we deliver as a 1U console on this platform a database migration product called Mosaic Dart, and that's a high-speed movement and transport software platform that will reach out to either big endian, little endian, older platforms, and through point, click, and ship, orchestrate the movement of the database to this new Oracle RAC platform. And there's also a web-based console that provides real-time health alerts for all the hardware and software and switching components. So these are some of the more detailed view of the components. Again, one way to logically or conceptually break this down is that there's a compute, interconnect, and storage piece to the solution itself. This implementation for this client happens to use Dell PowerEdge R740 for the Oracle RAC node, and it uses what's called R740XD, the Dell PowerEdge servers for the storage as the storage nodes, and it uses the Mellanox SV7800 EDR InfiniBand switch and the ConnectX-5 cards that are key to the solution. The OFED drivers, another key piece to the solution itself, which are installed. This is all pre-installed, pre-configured, set up. You just plug it in. There's a quick survey. We take some configuration information, and it gets shipped, and you plug it right in at your destination. And then, of course, on the NVMesh side, we have Excelero NVMesh core software. We have it on the compute and the storage side, which is the key storage software technology that's pre-installed, pre-configured, and ready to go. Some of the features, it's ultra-low latency. So again, we're taking what is traditionally a millisecond, a couple milliseconds for kind of large block I/O, and bringing that down to 30, 40, 50 microseconds of latency. This is a simple yet elegant. In other words, relative to, for example, something like Exadata, we don't have a large, complex set of software on the storage side. Rapid deployment scales out, comes in small, medium, and large. It is all pre-installed, pre-set up, the Oracle RAC cluster, the clusterware, ASM, all the storage volume configuration, even up to the databases can be created before shipped. As I said, the point-click migration with a Dart tool that we ship with it. And it's a fully redundant platform. There's no single point of failure. All the components in the storage, interconnect, and compute are fault-tolerant and redundant. And most importantly, because of the protocol enhancements, because of the Mellanox features and the overall features, it has compelling price performance, because the key thing is NVMe, unless it's end-to-end NVMe, is not NVMe. By that I mean if you have flash technology and NVMe on the storage array, but you don't have it coming in on the compute rack node, you can't get 40 gigabytes per second on the rack node. In our solution now, we're getting over 45 gigabytes per second of scanning on a single rack node. That allows us to reduce the rack node and the Oracle licensing costs significantly, which is a key feature here. And as PCI Gen 5 comes, and as we get to 200 gigabit and 400 gigabit, as PCI Gen 5 comes out, we will continue to increase this and be able to drive excess of 50 gigabytes per second or more into a single rack node. How did we get here? We kind of went through three major generations. One, which is a large storage array on the back end with the Oracle Rack Cluster. Second generation was an original vendor that was more PCI attached NVMe called DSSD. And the third generation, which is where we are now with the Mosaic SD NVMe, which is NVMe over Fabric, leveraging the NVMesh and the Mellanox technology. And there's several advantages to this third generation over the generation 2. In addition to the bandwidth and latency, which is, are both comparable, there's a lot more flexibility in Gen 3. In other words, we've decoupled kind of the hardware and the software. So as the hardware advances, PCI Gen 5, the other advancements take place in InfiniBand and the Ethernet space, the transport space, we will continue to be able to leverage those advancements and not have to be stuck by a kind of a hardware and software attached solution. If you take a look at some characteristics of this technology, though, the storage protocol originally was fiber channel, which is still a very, very prevalent protocol out there. The problem with fiber channel is you can't get as much through the fiber channel protocol. That's where the end-to-end comes in. Then we went to PCI direct attached, and then the most flexible and kind of cost-effective, the NVMe over Fabric, which is what we have now. The scalability, some of the characteristics of this on the storage side of the scalability is kind of that first generation high-end array. At any high-end array, this generation is limited by kind of this monolithic storage technology. It tends to be expensive to implement, and it oftentimes can use certainly proprietary software and hardware as part of the solution. The DSSD was a step in the right direction. It was a smaller form factor, went from 3 racks down to 1 rack, but it tended to be more expensive, and it was more limited by proprietary hardware and firmware that's out there. So again, where we are now is where we want to be. This is fluid, inexpensive, easily scales up from small, very, very quick to add on-the-fly nodes and to expand your fabric, and it can use commodity compute, storage, and also commodity software, open source software. The performance, again, we see just great performance. If you look, we're down again in the 30 to 40 to 50 on the high-end storage arrays on the left-hand side, the performance and the bandwidth itself. And over on the Mosaic SD NVMe now, we're up in the 150, 160, and actually which would be close to 200 gigabytes per second with the latest Dell 740XT servers that actually increases the number of PCI lanes that come out of the NVMe drives itself. So, we're building clusters right now that are up to 200 gigabytes per second, able to deliver off 8 storage nodes. And again, power comes down, and most importantly, when you take a look at that price performance, it's just much cheaper to provide that capacity on the platform we're on right now. So what are some of the numbers of the proof of performance for this high-end customers? Well, what we did is we went out, and there's 2 things we did. So that we did with the customer did. The first thing is there's a set of benchmarks that the customer runs that they call the atomic Oracle benchmarks. These are kind of enabling benchmarks that if you can do this for high-end analytics on an Oracle RAC platform, then you're going to have a great ability to service thousands of customers of very large databases. So we ran some of these Oracle benchmarks, and some of the results you see on the screen itself. And this was for an Oracle RAC node, 8-node RAC cluster with only 8 Dell 740XD storage nodes. I have to say that this, for the newer customers that we're shipping to now, we're actually reducing that Oracle RAC count more significantly, because traditionally in the past, people have proliferated RAC nodes just because they could only get a certain amount of I/O bandwidth up into a RAC node. It wasn't a compute or a memory issue. It was really a bandwidth issue. And that had to do with the protocol that's being used, the fiber channel protocol, and what you could push through 16 gig or 32 gig fiber channel. Even if you had it on the back-end storage rate, it's a compute node issue. It's an end-to-end issue. So we're seeing direct path read time for an 8K block of under 100 microseconds that the customer is seeing now. This customer scans up to 685 terabytes per day. Each hour, they're scanning for this one analytic database on this platform, 137 terabytes. Scanning trillions of rows per day, 2.5 trillion rows per day they're actually scanning. So massive amount of use on this customer right now. Some of the atomic operations, in addition to the general benchmarks, they were able to create a global unique partitioned index on an 8 billion row fact table in 2.3 minutes, 8 billion rows, and a direct path partition insert on 8 billion rows, moving it from one source table to one target table, which is one operation they need to do. 11.5 terabytes of table, selecting it from one, moving it to another in 60 minutes. They were able to do that. And they're able to scan that single table, 11.5 terabyte scan time in a little over a minute, which again gets back to that original I/O problem. If that scan time was more like traditional 30, 40, 50 minutes, that makes some queries, that makes it kind of untenable for the query population that's there. But if you can scan it in a minute or 45 seconds, you just have a lot more flexibility. And then finally, the aggregate sustainable scan rate for this customer, about 154 gigabytes per second, which actually is on the low end right now for ones that we're shipping. Okay. This just gives you an idea of actual real-world queries the customer's running. This is from a product called OBIE. This is Oracle Business Intelligence. This is the traditional, for this customer, the traditional type of query that's been built and it's running for them for thousands of users running on this platform. And with most any database, 80% of the processing is localized in the larger fact tables in this high-end space analytics. So that's the area. That's the area. So they're oftentimes joining this claim trans and claim proc and claim DX. These are medical. This is in the medical space, which are really joining a 13.5 terabyte table to a 1.1 to 1.4 terabyte table when billions of rows being joined in this. And this is just one query. There are thousands of these run by this customer in a day. Okay. And what is the typical usage statistics? Well, they collect them every day, and every day they're what you see. And we show you 2 days here, 2 days of them running it. This is what we see. For these very complex analytic queries, we've broken down the response time that they sent us, that they collect every day and they keep track of. And they broke it down into 4 different categories. On day 1, you can see that over 629 queries, or over 91% of the queries for these complex, the ones I just showed you type, are returning in less than 1 minute, less than 60 seconds. And this is from a tool that's just generating this, queries being generated by OBIE. Then they get up to almost 99%, 98% of 650 plus queries, right? 650 plus queries are returning and all running simultaneously over the course of the 8-hour day in less than 3 minutes. And on the second day, we see the similar thing. We just see for these very complex queries, upwards of 99% are returning in less than 3 minutes. And these traditionally, if you were to go out and take a look at the database this size on a lot of Oracle RAC platforms, on traditional platforms, you would probably see this go out to 2 to 3 hours to 4 hours, and you'd see a much flatter curve. So this is kind of, very, very impressive performance for this type of workload coming at this platform. Remember, this platform is sitting in 142U rack. That's all it is, 142U rack delivering this. Okay. And this is about it. And thank you very much for being able to present it. I'll turn it back over to Tom.
All right, Brian, thank you so much. Very, very informative as always. We got a good amount of questions here. Let me kick it off with one from Rajesh. This one is probably for John. What is the difference between NVMe and NVMe over Fabrics, and does Mellanox support NVMe over Fabrics?
All right, I think I'm unmuted here. Thanks, Tom. So NVMe is the standard for accessing the drive, these new flash drives locally. The standard is about 4 or 5 years old, and it's very common, supported by pretty much all the operating systems and servers, and it's used to access an NVMe SSD locally over the PCIe bus. NVMe over Fabrics takes the same protocol and extends it over a network and it can be an RDMA network. That's what's most commonly used, like InfiniBand or Rocky. It can be over fiber channel, or it can be over, most recently, TCP on Ethernet. So Mellanox supports both. We support them. The NVMe over Fabric we support with both InfiniBand and fiber channel, and then NVMe over TCP we support with over Ethernet, of course. We don't do fiber channel, but anyway. So it's the network version of NVMe and what NVMe over Fabrics is.
All right.
Cool. Yeah, and John, if I could add, Tom, so in our solution, there's 2 different NVMe over Fabric protocol solutions that we support. We support an all InfiniBand solution, and we support a Rocky V2 solution, RDMA over Converged Ethernet. So it depends on what the customer's preference is.
All right, cool. Thank you so much. Next question comes from Dan. Does CMA's Mosaic support Ethernet RDMA 2 or just InfiniBand for the networking?
So that's a good question that we just spoke about. So we support the all InfiniBand, and we support a solution NVMe over Fabric of Rocky V2, both. The configuration is a little different, but from the Oracle perspective, we configure support both. It just depends upon, it's an internal to the product itself, right, that Fabric is, but we support either one.
All right, good, thank you so much. Then I got 2 questions from Philip. Probably also for Brian. First question is, with multiple servers accessing the same disks, how is cross-node locking handled?
So the same way that Oracle handles contention or concurrent access to a block is handled in this solution. So in other words, it's transparent to Oracle other than kind of some of the underlying semantics or the delivery economics change. But Oracle is still using Cache Fusion. We still have the set up, and in this configuration that we have, we're using InfiniBand for the interconnect. So really the way Oracle manages in their wait events, the GC, the global cache wait events, and the Cache Fusion technology, and the HAIP configuration, and again, the way that the Oracle rack nodes share the block does not change. This does not change it because it's underneath that clusterware layer, and the clusterware just sees, albeit higher bandwidth and different speeds, it really just sees the same thing that it sees with traditional Oracle rack implementations.
All right, and then another question from Philip, and Brian, you may want to get into the Q&A box here to make sure that you understand the question right, because I'm not sure if I'm going to be reading it right. Does the rack Cache Fusion GC events overhead increase or decrease with Excelero in an OLTP environment?
So the overhead does not increase. In fact, it decreases. And it decreases to a certain extent because the kind of the semantics or the speed and the delivery of the blocks are just much quicker. So if there is something that requires if it can't be shipped over, let's say, point to point, node to node, and it has to be pinged out to external storage and then reread in, that process just happens much quicker, much faster, relative to the interconnect speed. So what's happened is the storage fabric latency is now much better aligned with that cache fusion, right? The amount of time it takes to ship it over across from compute node to compute node. So we are seeing certainly no increase in the preponderance or the number of events of those type, and we're certainly not seeing any more overhead for those GC events either. Those wait events and the prevalence of those wait events is a kind of a significant asymmetry between different pieces of the overall solution that are much less capable or have a much wider divergence of their ability to be able to work cooperatively together. But this actually kind of converges the storage and the compute a little bit closer.
Okay, good. Thank you, Brian. And then that one's going to be for you again. I actually got a similar question from several folks. So I'm going to read one from another Philip here.
I see it.
But from multiple people. Are the Dell 740 servers the only compute and storage products qualified for the Mosaic as the NVMe cluster?
No. No, really. There's a couple key components that we require in part of this solution. One is that either Red Hat or Red Hat Linux in a certain release level, or UEK kernel in a certain release level, and that Linux layer kind of gives us kind of a wrapper that binds around x86 hardware, whether it's Dell servers, HP servers, Lenovo servers, Western Digital Storage. It really doesn't matter. As long as what matters more is the key pieces to this, in addition to Oracle, are the NVMesh software. That's the key scale-out piece. The Mellanox drivers and the Mellanox ConnectX-5 cards and the Mellanox switches are critical pieces to this. And the PCI lane, especially on the storage side, the PCI slot capability and capacity. What we don't want is necessarily thick nodes that have the proprietary processors and have even lots of memory. Really, what we want is a very capable PCI internal networking, so that we can leverage the capability and the ultra-low latency of the NVMe drives themselves. In other words, you're dropping these NVMe drives that are very capable, and every month or 6 months are becoming more and more capable. And to exploit the bandwidth out of those NVMe drives and get them up into the rack node, we need to have a good PCI architecture, PCI fabric, from the X4 NVMe drive up into the front-end Mellanox card itself. And the I/O is bypassing the CPU on that storage side. So really, the path goes from the NVMe drive up to PCI fabric, out the card, over to the other card on the compute side, and then up, then directly is addressable by the Oracle process itself. So PCI architecture, very important in this solution, but we don't care really what the vendor is, and we've had 4 or 5 vendors that have been qualified.
Yeah, and I would like to add to that for the Excelero NVMesh solution, we have a great configurator on our website under the product section. So on excelero.com, where you can actually see the performance that you will be getting pending which hardware that you will be selecting. And most of that hardware will then also support the rack architecture. All right, thank you again, Brian. Question from Kathy. How does the rack setup differ from the traditional setup with external storage arrays?
So from the Oracle setup itself, it's actually a little simpler, I would say. And one of the reasons it's a little simpler is that kind of the precursors or the dependencies that the Oracle RAC cluster has are simpler to set up. In other words, the storage configuration is simple here. The storage software setup is simpler here. It's much more adaptable and fluid. What happens is when the volumes are built with the NVMesh on the back end, the software-defined volumes, and they're exposed through the network, they're exposed to the Linux rack cluster as block devices. So the Linux cluster just sees them as another block device, a very high-performance block device, and then that's presented up into ASM, and just like any other disk would be presented to ASM, and it's ready to go. So the storage configuration is actually quite simple, very easy to set up, and from Oracle's perspective, ASM and the clusterware are just seeing regular block devices, although the NVMe client-side drivers are key to this, sitting on that client side. They're actually very key to this, but it really doesn't change the Oracle configuration at all. In fact, it's very, very simple. The other thing I'll say is that it actually also simplifies it because in our configuration, typically we'll use, we simplify or we unify through the same Mellanox switches in the Mellanox hardware architecture. We're kind of overloading that. So we're implementing both the interconnect through the InfiniBand, and we're implementing the storage fabric through the InfiniBand. So actually from that standpoint, you're actually simplifying the setup for the Oracle RAC cluster itself because you're taking advantage of the ability to overload that, essentially the networking architecture, leveraging both the Mellanox technology, the drivers, and the NVMesh solution. Now, I should say one thing. Now you can protect the storage again. You can protect the storage externally, various ways with the NVMesh software, so you can get protection there, whatever your preferred method is. RAID 10, mirroring, whatever that is, and erasure coding soon. And you can also choose to stripe externally and use ASM mirroring for protection. And we have customers that prefer one over the other. One uses one method and prefers it for, they've gone through the calculation and there's reason, and others prefer to protect it externally. So we support both also. That's part of the information we gather prior to building it, what your preference is on that.
All right, great. Thank you, Brian. Here's another question from Jim. What's my cost and performance benefit or loss versus a full Oracle Exadata stack?
So there's similarities with Exadata and there's differences. And cost is measured, can be measured on a couple different fronts. Let's just take kind of capital price performance, and let's take operational or maintenance. And let's also talk about qualitatively what maybe a difference is. The real value add of, and this is, if you take a look at Exadata and you take a look at this Mosaic solution with NVMesh, and you take a look at all the other rack clusters that are out there running with the traditional storage arrays, the one advantage that both Exadata and Mosaic SDNB have is the ability to concentrate, is to reduce that Oracle rack node cost. And Oracle does it by Exadata by pushing out a lot of software onto the server side to push that predicate filtering out at the point of where the data, when it can, but it can't always do that. That's the problem. What we do with this solution is we leverage this great technology, and we leverage the hardware and the advancements in the software to be able to push 50 gigabytes per second into a rack node. So traditionally, if a large storage array vendor needed to hit 100 gigabytes per second, that's what they needed to hit in aggregate across the rack cluster. they'd have to put a lot of rack nodes. They'd have to put 8 or 12 rack nodes out there. But we can hit that in 2 rack nodes. So from an Oracle licensing standpoint, we're actually significantly cheaper than most vendors that are out there, and Exadata is an example through other technology where they can also reduce that client rack node cost. We are a more open platform and a simpler platform. We're using vanilla Oracle per se, right? It's just the Oracle that everyone uses and everyone loves and building their own solutions, and that's exactly what you get here. Exadata, you have to license the storage software. There's a lot of software that's only on Exadata, that's not on the vanilla Oracle, that is part of the solution. You have to pay for that, and they have to maintain that. They have to maintenance it, patch it, and their certified stack becomes more complicated. Ours is a simpler stack to manage. So from a maintenance and a patching standpoint, ours would be a cheaper solution. So that's some of the differences. The other thing is, when we deliver this solution, remember, we deliver 2 things with it that are key. We deliver this migration tool, this Dart tool, that doesn't care where you're coming from, as long as it's an Oracle database of 10, 11, and 12, and through a point, click, and ship, it'll move up to 10 terabytes if the networking is there per hour into this new platform, without any code, any binaries, or anything like that. And we provide this NVMe console that sits on top of this Oracle compute cluster in a box that provides all the hardware event monitoring, all the hardware state information, and also integrated Oracle performance information on the platform itself. So, and we provide services to kind of go up the stack. And Oracle tends to come in, and Exadata is a great platform, drop it in with people who install it, and then tend to go away. So I'd say that's really another difference also.
All right. Brian, John, I'm going to thank you here. We're getting towards the top of the hour. I had a few more questions, but I think people have to run to other meetings. Again, John and Brian, this was great. Thank you so much. I hope to do a next webinar sometime with you guys, because it was very informative to the audience, or what's left over right now. Thank you very much for attending. A recording of the webinar will be put online, and you will get a link to that if you want to review certain sections. Thank you very much, everybody, and have a great rest of your day. Bye-bye.
Thank you, Tom. Thank you, Brian.
Thank you. Thank you. Thank you, John.